So, as promised in the last outing, in the last lecture, today we'll talk about escape speed. That's also called velocity sometimes, but that confusion should be understood very well. It's basically a escape speed. Now, suppose, say, daily experience that we throw an object from the surface of the earth up. Okay, so it goes, its velocity keeps on decreasing due to gravitational force on it, and after reaching a certain height, h, from the point of projection, it stops momentarily and falls back, tracing the same, or in a projectile motion, it can come back to the level of projection, to the earth. And we know that if we increase the velocity, then the object, the projectile, the projection goes up and up and up. But most of the time it falls back. Now that is because of the conservation of mechanical energy. That is, the principle of the conservation of energy, the principle of conservation of energy helps us to understand this phenomenon. So, on this path, if the projection is vertical, from the time of projection till it falls back, everywhere the law of conservation of mechanical energy will hold. That is, the kinetic energy plus the potential energy as described is a constant, is conserved. Okay. But if we have the prowess, if we have the technique to increase this velocity to the extent that my projectile, my object, which we project from any level near the surface of the earth, it goes and goes and goes and goes and does not come back. It does not come back. That means it escapes. It escapes the earth's gravitational field. The same is true if we deal in any other planet, any moon of planet, then also the same thing is true. So the first thing which has to happen is that the velocity should be such that it goes and goes, and we can say that it has gone to the infinity. Because we are building up a theory, therefore we say it goes to infinite distances, where the velocity may be zero or the velocity may be non-zero. So that velocity, I will, when the object reaches infinity with a speed Vf, the minimum value of Vf has to be equal to 0. Else it can have a speed more than 0 and the projectile has been launched, and then let us see as to what happens, what kind of a mathematics we get. And it's very easy, very simple. Total energy is equal to kinetic energy plus potential energy is equal to capital E, like here we say, and that is the constant for the system. Constant for the system is that no part of the kinetic energy is converted into heat, into light, into sound, into any other form of energy. So we are taking the situation, ideal situation, that there are only two kinds of energies associated with the system. There is our planet, maybe planet Earth, or any other heavenly object from where the thing has to be projected. So what we get is, at infinity, the total energy of the system will be equal to W1. Remember, we talked about the W1, and that is the gravitational potential energy at infinity. Okay? Which we very conveniently took to be equal to 0. No problem, but still we'll stick to that W1. So I get the E infinity as equal to W1 plus the kinetic energy of the projectile at that distance away from us, half mvf square. So this is one equation that we get for the projectile, for the object that we want to escape the earth. This is equal to W1 plus half mvf square. Don't worry about W1. Okay? Now, if we project the projectile from a height h above the surface, normally it is a few hundred meters, okay, so that if r is the radius of the earth and h is the height, then its distance from the center of the earth becomes equal to r plus h. Okay, no problem. So we write the total energy at the point which we describe at r plus h. This is because half mvi square, where vi is the initial velocity of projection of the projectile, has to be equal to or more than the escape velocity, which we are going to discuss shortly. Okay? So half mvi square, the initial velocity, the kinetic energy associated with the system, minus gmm upon r plus h, which is the total potential energy associated with this r plus h. Okay? Of the mass m, because of the earth or whatever planet we take into consideration, or moon we take into consideration, plus of course our W1, which is the gravitational potential energy at infinity. So I get the equation E like this, ER plus H. Now, the conservation principle, and the conservation principle says that this expression must be equal to this expression. So let me write this expression over here. Of course, I should have had a W1 here. Okay, W1. And I should also have on this side also plus W1. But these two W1s, they cancel out, and that is why initially I didn't write this equation. So it turns out to be equal to half mvi square minus capital G mm upon r plus h. This is equal to half mvf square, which is the kinetic energy of the object at infinity. At infinity. Because it's kinetic energy and this is Vf square. M is a positive number, so this whole thing becomes positive always. So this is positive, means it is greater than 0. Okay? So I can write from here just that I have the equation half mvi square minus capital Gmm upon r plus h is greater than 0. Okay. Well, it is greater than 0 when Vf is equal to more than 0. I'm sorry. Okay? Since it is positive, this has to be more than 0. Yes. So, if Vf is equal to 0, if at infinity the body is moving with a 0 velocity, if like this, then I can write simply that we talk in terms of Vi minimum. The minimum velocity with which we are going to project is half mvi minimum square is equal to capital Gm upon r plus h. So this value I can write from this relation readily, that 2 will come on this side, m and m will cancel, so it will be what we have is 2gm upon r plus h. So here it is an r plus h, okay, it should be r plus h. So this is what is we call the escape velocity, and this is equal to under root 2gm upon r plus h. But because r is a few hundred meters maybe or less, therefore we say that r is very, very large as compared to h, and therefore I can brush aside, go away, okay, because this is negligibly small, insignificant as compared to r, and therefore we write this relation that V escape here, the escape velocity is equal to under root 2gm upon r when h is very, very small. This, look here, in this expression, if I here multiply and divide the numerator, and multiply the numerator and the denominator by r, then this becomes equal to 2gmr divided by r square, and gm upon r square becomes equal to small g. Okay, so okay, I'll write because the space is not there, so I'm going to write it. So well, we did calculate that the escape velocity is equal to under root of 2gm upon r, when of course h is very, very small. So we are projecting the projectile from near close to the surface of the earth. Okay. So it is V escape is equal to under root 2gm upon r. Now I said, and I am multiplying this by r and this also by r. So I get minus 2gmr divided by r square. See, and this is our friendly thing that we have known for many, many years. This is what we call the acceleration due to gravity at the surface of the earth, which we presume to be the same all over the earth, okay, and particularly at the sea level. All over the world we think that the earth is a round, beautiful football type of object, and then we get it under root 2gr. Now I just substitute the value of r is equal to 6,000 kilometers, approximately kilometers. Okay, this is the value of r, the radius of the earth. So I substitute this 2 into 9.8, the value of g at the surface, multiplied by 6,000. I am writing like this, 6 into 1,000 kilometers, and then I am writing another 1,000. So I get it. This is 9.8 into 12. Okay, under root into 1,000, which I take out of the root, and meters per second. Now this turns out to be equal to approximately 11.2, and therefore the value of the escape velocity is 11.2 kilometers per second. Sometimes I make mistakes, you make mistakes, that you call it in a flow 11.2 kilometers per hour. No, 11.2 kilometers per second. So this is the value that is there. So any object which is projected from the surface of the earth with a velocity equal to 11.2 kilometers per second will escape the Earth's atmosphere. And the Earth's atmosphere, it consists of gases. It consists of even water vapors and many other things, and you know that as you go up, 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 then it is rarefied. Okay. But the gases don't take a ride. Don't say that, okay, let us go somewhere. Let's have a good time. No, they can't. Because their average kinetic energy of the molecules of the gases at the temperature, pressure conditions that we have, we'll see about that when we talk about gases and the kinetic theory of gases, we arrive at that result. That will be less than 11.2 kilometer per second. Be it helium, be it hydrogen, be it oxygen or carbon dioxide or ozone, anything, it's not going to escape the surface of the earth. Okay, so our atmosphere is maintained. What happens if we take barrels and barrels of nitrogen and oxygen, okay, and take them to the moon? We are traveling to the moon very often. Even we in India, we think of traveling to the moon. What is the problem? We are taking the gases. When we go there, we take the oxygen, we take the water vapor, etc., etc. But we find that the funny thing is that at the temperature and pressure that is there, whatever temperature is there, the gases will escape the influence of the moon. From the moon they will go for a ride in the vast space, wherever they want to go, molecules. The gases will escape the moon, and therefore if we have a flag on the moon, it will not flutter. So if the flag flutters, then people have doubts as to whether the project was a successful project or not. I'm smiling, you may also smile. So anyway, what is important is that from anywhere, when you are coming back from the moon, then again you have to think of, you have to make a blast to obtain kinetic energy for the object to come back towards the earth, and then they have, we can calculate it to be smaller than 11.2 kilometers per second. Not much smaller, still in several kilometers per second, but coming back from the moon or coming back from the Mars, whatever, it always requires there a mechanism where some kind of a energy transfer takes place in very short duration of time, and we are the object which has to be sent back. If we want to come back, the object which has to be sent back has to be projected from there with a velocity which is more than the velocity of escape from that planet, or from that moon, or from that body, whatever is there. So this is a very interesting subject. We must have rockets, we can propel the things with such high speeds, and we must have fuels which can provide that instantaneous energy, etc., etc. We'd like to control that, and that is how the space travel is possible. What you have to do is, when my projectile is going out of the influence of the earth, then after that it may be under the influence of the gravitation of the moon or whatever. We can discuss that in an exercise later on, but for today I leave you with the discussion about the escape velocity, escape speed, and why it is so. That, as I told you, I am just going to repeat, if this is the surface, and from this surface the projectile has to be projected. It can be projected in any direction with the same initial velocity, and it will go out of the influence of the earth, whatever way. Why it is important? Because this velocity here that is there carries with it an energy half mv square, which is a scalar quantity, and it doesn't matter whether we project it vertically upwards or in certain direction. It all depends upon where we want our projectile to reach. Okay, so with that I wind up, and we'll talk next about satellites, which are of course, one satellite that we see in the Earth system is the satellite called nature-made satellite called Moon. There are other satellites also which have been, we have been able to put them in orbits. The orbits are close to the surface of the Earth. The orbits are at certain heights, a few hundred kilometers, etc. And the orbits are very high altitudes when we talk about geostationary satellites or parking satellites, which go around the equator, and they can be seen from anywhere to be stationary with respect to us. That is why they are called geostationary. Thank you very much.